Now today let's go with very important basic concepts, covariance matrix. This is very important to identify the relationship with one dimension to other dimensions. For example, when you have a distance and speed, the relationship between distance and speed, and then distance to the speed is the covariance. So with respect to data, now we it's very important to identify the covariance matrix, and let's go step by step. Now, if you see, for example, covariance matrix given as such a matrix like this, and it's like ABC are the dimensions. So in these dimensions, you want to find out for a given set of data, what is the relationship with A and B and C. Now let's say if A is the distance and B is the speed, and then C is time. So when distance is more with respect to time, then the speed is more. So A and B are proportionately relevant to each other. If A is increasing and B is decreasing, it means they are inversely proportionate. So in order to identify the covariance, we use a technique called covariance matrix. And this covariance method is already available in NumPy library. So we import the NumPy library. So these are the different dimensions, and we convert this dimension into a single matrix. And this matrix, we call this covariance, and then we use bias. Bias is a very simple concept. So with respect to graphs, so you can make a Google search what is a bias, you will get to know about it. It's very simple concept. So that's why I'm not touching this bias. So when you run this covariance, you can see the covariance matrix. See, if the number is very large, it means see, if you see these diagonal matrices, so these diagonal matrices is further with respect to its own dimensions. So this is nothing but the relationship with A, and relationship between B, and relationship with C and C. Now this matrix is the relationship with B with respect to A, and this is a relationship of C with respect to A. If the number is large, it means the variance is very high, and if it is positive, it means proportionate. If it is negative, it means inversely proportionate. So this is the formula for covariance. So let us go touch base, see what is the how the covariance is actually calculated to understand about regarding the covariance. So this is our data. So if you see our data, so A dimensions, B dimensions, C dimension, the matrix has come like this. But this is not the proper way to represent a matrix. The proper way to represent a matrix is like this. Most of the algorithms are having this kind of a matrix. That means the dimensions are in columns and data points are row. If you want to have a data points on columns, then you have to change the entire algorithms, because most of this one is based on the it's based on different representation. So this is our way of representation, but NumPy took a representation like this, like dimensions in a row wise and data sample in a column wise. So NumPy is able to calculate the covariance in this manner. So normally most of the algorithms, what we do is we make a column as the dimensions. Now let us have a convert this, we make a transpose. Transpose means interchanging the rows with columns and columns with rows. So when we do interchange this B, so B is nothing but this kind of a matrix. So there is a formula for matrix. So formula for matrix is this X, whatever you have a column vector means all the values that is represented in a single column is separated by the mean, separated by the column mean. I think in the first session I have explained how to calculate a row mean or column mean. So since we are going for a column vector representation, so we are going column mean, means. So what we do is we take the means with respect to column. So that's why we use axis 0. So we got the means of the column vectors. Now what we do is we separate these column vectors with the means, When you separate the column vectors with the means, we get the differential matrix. And this differential matrix, what we do is we will multiply with its own transpose, with the transpose. So why we do this? If you see here, x and y are two different matrices, but for covariance, here in this covariance we are checking for the same matrices, so it is nothing but you are squaring them. So that's why you are having a this difference transpose, you are taking the dot product of difference transpose with respect to difference, and you divide it with number of samples. So number of samples means number of data sets. So we divide with number of rows data sets. When you do that, you get the same covariance matrix which you get it from the library here, the same one. So we can print it together. We can take this, and this is our covariance matrix. So let's print this one. Okay, this is okay, this is with bias equals to true. Let us have this one here. Since I was running multiple, so that's why there is a bias parameter interchange. Now if you run this, okay, you can see this with the help of NumPy you are getting the same covariance matrices. And now we'll see how we have to analyze the covariance matrices. Now earlier I have explained, apart from data analysis, it's also important to draw graphs. So for covariance, what we do is we do the heat map. So in heat map, we can see with respect to the colors, see diagonals is related to its own elements, so we can ignore the diagonals. Only thing what you see is the representation of B, the relationship with B respect to A and the A respect to B. Relationship of C with respect to A and C with respect to A with respect to C, and this relationship between B with respect to C, and this is relationship between C with respect to B. So that's why you can see these values, corner values are same. So it's here it is positive, so the relationship B and A is positive, so it's there proportionate, it's like speed and distance. Now this is negative. Negative means they are inversely proportional. It means when B is decreased, C will be increasing. If C is decreased, B will be increasing. So that's they are inversely proportionate. Now here, when A will increase, B is increased. So we are analyzing what is the relationship with of one dimension to other dimension. Okay. Now earlier we have taken bias as true. Now I told you that bias is a very simple concept. I am not going to touch it, so you can go for Google search. Some of the very basic concepts I am just leaving up to you so that you can learn it. I cannot touch each and every basics. So if you have a bias as false, you can see you have a different covariant matrix. So little bit difference. So here you have 12, you have 15, you have 6, here you have 9, and 9 here and 12. So little bit difference because of the bias factor. So some of the cases algorithms you consider bias, and some of the concepts you don't consider bias. If bias is false, it means the boundary decision goes to the origin. That's what it means when bias is false. When bias is true, it means the boundary decision is not passing through origin, something like that. It's not necessary, but just to explain a little bit about the bias. Now similarly, apart from NumPy, we have extremely powerful open source library pandas. So I'm not going to give you the syllabus for to cover basics of NumPy and pandas. I just want you to go through the Google so that you will know what is pandas and NumPy. So in pandas, it also gives you covariance matrices. So you can see this is how it has printed covariance matrices. So both are different libraries, but you have multiple variations between those two libraries. Depending on your usage, you will use it. So now what we are doing is, now we are having the heat map when bias is true. So here we are using SN heat maps of covariant matrix, and here covariance is similar to this. So by default the bias is false because we are not passing bias. So when bias is false, you can see the number values are different, but the still relationship is same. So negative means inversely proportionate, and this is proportionate, positively proportionate. So this is about covariance matrix. Thank you for your time.